So our task now is to work out how we arrive at the general solution to this second order differential equation. So we're going to start off first of all by making this thing easier to look at. So for simplicity, I'm going to say let alpha equal to P over EI, and I'm just going to replace the second derivative of V with alternative notation. So we're going to say that is equal to V prime prime. Okay, so very typical notation. So rewriting the equation, we've got the second derivative of v with respect to x plus alpha times v equal to 0. And this is an equivalent starting point. It's the same equation, it's just written a little bit differently. So what we have to do now is find a candidate solution. That's typically how you start off solving these kind of questions. You try and find what is a function, right? What is a function of v that would satisfy this equation? And what that really means is I need to find some expression for v, some function for v, that when I differentiate it twice, I'm still able to add or subtract it from the original function. So if you think about that for a second, when we differentiate a function, we usually change it fundamentally in a way that would make this simple addition or subtraction not possible anymore. Fortunately enough for us, there is such a function. So if I was to start off and say, let v equal to e to the power of some constant lambda times x. Okay, so this is typically worded, if you see this written in a maths textbook, or if you cover this in a maths lecture, what they typically say is, let's assume a solution of the form v equal to e to the lambda x, right? And all that's really saying is, let's try this function, because this is a function that when I differentiate it twice, I can still add it to the original function, okay? Because if I look at what the differential version of that is, or the differentiated version of that function is, v prime, the first differential, is just going to be lambda times e to the lambda x, and the second differential is just going to be lambda squared times e to the lambda x. So that's a good starting point for me. Our next stage, or our next step, is to take our candidate solution, right, our candidate function, which is this guy here, and sub it into our differential equation. So that's what we'll do next. So we'd end up with lambda squared e to the lambda x plus alpha times e to the lambda x equal to 0. And we can factor out the e to the lambda x. This is typically referred to as our characteristic equation. Now remember, we're trying to solve this equation. So we're looking at this and we have two elements here that multiplied together equal 0. So that means one of those things equals 0. Either this equals 0 or this equals 0. Now we know e to the power of something, some non-zero number, is not equal to 0. So that means the thing in brackets must equal 0. So we can say that lambda squared plus alpha is equal to 0. And if we follow that through, we're going to essentially solve for alpha. So we can say that, or rather we're going to solve for lambda. So we can say that lambda squared is equal to minus alpha, which means that lambda is equal to plus or minus the square root of minus 1 times the square root of alpha. Now we know we can replace the square root of minus 1 with I. So we can say that lambda is equal to plus or minus I times the square root of alpha. And don't forget, alpha is just a placeholder here. Alpha is P over EI. So we have two possible solutions for lambda. We have lambda equal to I times the square root of alpha, or let's call that lambda 1. Or the second option, lambda 2, is equal to minus I times the square root of alpha. So subbing our values of lambda here, this guy and this guy, back up into this equation, we end up with our general solution. So replacing our alphas, or rather replacing our lambdas, we have C1 times e to the I square root of alpha times x plus C2 times e to the minus I square root of alpha times x. Now that's not quite the general solution that we're looking for because we still have these I values in here. So we're now going to use Euler's formula to get rid of those I terms. So we know it's a known relationship that e to the I times x is equal to the cosine of x plus I times the sine of x, and e to the minus ix is equal to the cosine of x minus I times the sine of x. So this is from Euler's formula. So that means e to the I times the square root of alpha times x, using Euler's expression, would be equal to the cosine of the square root of alpha times x plus I times the sine of the square root of alpha times x. And then similarly for the negative, e to the minus I square root of alpha times x. So now taking this guy and subbing back into our general solution, okay, so we can then collect up our cosine and our sine terms. Okay, so you still have these C1 and C2s and you still have an I in here, but if you think about it, they're just constants. So I can just, arbitrary constants, I can just replace that by another arbitrary constant C1, and I'm going to replace this with another arbitrary constant C2. And that's how we end up with our general solution to the differential equation. And don't forget, obviously, we've made the substitution for alpha here, remembering at the very start that alpha was equal to P over EI. Okay, so that's a little bit of an aside from what we're talking about in terms of buckling, but that's essentially how we arrived at that general solution to that second order differential equation. So we can pick up the discussion now on determining these constants C1 and C2 for our pinned end condition.